Today we're going to see the root locus method, the basics of the root locus method, and how we can actually predict the location of the roots of the characteristic equation using a transfer function. So you can look at a simple example that I'm going to show you in here. Let's just get myself out of here. Let's say that okay, let me say that I have a, I need to do a need to draw, so I need to get one of these. Okay, let's say that you have a transfer function that looks like this. Okay, you have a transfer function, we're going to call it g of s like this, and if you have it like this is called the open loop. Okay, but if you look at the situation where you put a feedback loop to it, we could have a system, a basic system that looks like this. I'm going to draw a simple feedback control system. This is the input in here, and this is your output in here. So let's say that you measure the output and you want to feedback and make a comparison of the values that this obtains with some reference value. So this one in here is your reference. Ah, I think I'm trying to do something different. This is your reference. And then you can have in here a controller in here, which in this case we are going to use just a constant, a proportional constant in here. So if you have this, again, this is your output, this is your feedback, this in here, this is a control, and this is your system. Okay, so basically you can build a simple control system and study what will happen if you change the k values. That's what we are talking about. So let's see if we have this. Let's go to my PowerPoint slides in here, and let's start over there. Okay, so here's your transfer function. This is that k value in here. This we could call it overall transfer function, or you could say overall transfer function. Okay, so in here we have this this form, but what happens if we examine the roots of this denominator? This is the denominator of the transfer function, and this obviously is the numerator. Okay, so one of them could be here, the other here, and of the numerator over here. So if you have a system like this, for example, this is done for a camera system in here where you want the position of the camera to feedback. This is the transfer function of the camera, this is the controller, and so this is the overall transfer function. Okay, if you give some value of k in there, you're going to get different values for the poles. Poles are the roots of the denominator. And you could try it in several ways. For different values of k, you get this. But you see there's an underlining, you may say, growing this way, and then there's growing this way. There's a path. That path is called root locus. Okay? And if you consider something like this, for example, because it's factor, you can see this, from that comes this, from the other factor comes this, yeah? From the numerator comes this too, yeah? So if you change the value of k for this, you have this were the two roots and the two poles. If you change the value of k, you will get this. What is important, and in closing, what we're doing here is to go to MATLAB and actually get a transfer function to do. Where was it? I think it was in here, right? Yeah. So if we do that, you will see that if we get the transfer function in MATLAB, you will see that you get this root locus. So it means that it starts at the poles, goes like this, and then they continue going this way. And so this is all stable. You can say at any k. And that's what we're looking for. Okay, so we'll stop now.